Welcome to today's book club. I'm super excited to be here. And before we jumping into the topic, let's have a bit of introduction of myself. And I'm Kelvin. I'm a student at University of Adelaide. I participated the MSA last year. It was a very fun learning experience for me. And I got introduced to many different topics in technologies, and I found that machine learning was particularly interested. And that's why I want to be the speaker today to share my learning experience in machine learning. All right, I think that's enough for me. Let's jump into the topic. So in today's learning objectives, we will try to give you a more technical view in machine learning, but I will try to minimize the mathematics as much as possible so that it will not scare you away. And we will talk about different architecture in deep learning, and especially the generative model that we are going to try to implement in the Azure Machine Learning Studio. So the agenda for today will split into two parts. The first part, we will talk about the machine learning and the model behind the generative models. And then the second part of today's presentation will have a live demo of how to create the models in Azure Machine Learning Studio. So let's have an introduction in machine learning. So yeah, you can see right away from the screen this is a very cute, adorable dog, right? And by the way, this is my dog, and he is 5 years old. But in computers, this is very hard for computer to recognize these images because computer will understand only numbers and digits in a way that this particular part of the image will just be represented by a matrix. And this could be the RGB value. If you are familiar with the computer vision, RGB is the value of red, green, blue. And by combining these three numbers, you can create any color that you want. And we refer to each color will be a pixel. So for example, this particular part of the image will be represented by this matrix. And you can't really tell much from this number, right? And it's even harder, more challenging, because from a different viewpoints of the object, they have a different totally set of pixels. And this including the light setting. For example, like these images, they are referred to the same objects, but due to the lighting condition, they have a different set of pixel. And then we have different in the scale variation. I think right now the image normally will have like at least 1,000 of the pixels, right? But compare something that image have 2,000 of pixel, the arrangement is totally different. And then we have also different deformation of the images, even though they are having different pose, but they are referring to the same subjects. And then we have the background cluttering, which means they are very similar to the background. But what we are trying to recognize is the cat image in the center. And then we have different like inter-class variation. They are all different type of chairs. So it is very hard for the for computers to recognize these images, as well as just trying to identify the numbers in the pixels. And that's why we have to use machine learning. And machine learning is based on a data-driven approach. And for the task we will try and do is a class classification, and we have training image, and then we try to find a mapping function that can make prediction. And after it makes the prediction, we try to compare it to the ground truth, and then we will give back to the feedbacks to the mapping function and to tell them, can you do better? Can you do a better image mapping? So one of the very classical mapping function is to linear classifier. For example, we have, for the sake of the simplicity, we have this image here, but we just count it has only 4 pixels. And then we have a set of weights. What it is doing here is a very simple matrix multiplication. You still remember that? So we will slowly go through the step. What it's trying to do is we have 0.2 times 56 plus minus 0.5 times 231 plus 0.1 times 24 plus 2 times 2. And then we add it to the bias, and then we will get a score for each class. And then we repeat for the second class, we repeat it for the first class, and then we will get a column of the score for each individual class. And this is the, I think that was the most basic classifier we have here. It's just doing matrix multiplication, and then we get the score. What it is trying to do is we have pixel, and then we map it into the score for each class. And then the second step is we try to mapping the score into a probability distribution. And this is simply done by we take the exponent of each score, and then we sum over the sum of its exponent of each score, which in that case we have the exponent of minus 2.85 divide the other exponent score, and then we will get the probability distribution for this class. And take a note of that is this distributed probability distribution will sum into 1. And in this step, we're trying to mapping the score into a distributed probability. And then what we are trying to say to the model is, okay, we have the input image with doc, and then we have assigned 63% that prediction of this is a dog, and then 1.6% this is a cat, and then 35% for the car. And that seems like the model is doing pretty well. But however, we try to give the feedback to the model. So we need to do the one more mapping function to define how well is the model doing. And then the third step is to go into a loss function. And it's nothing really fancy here, where we just simply take the log of the ground truth prediction. And for example, we have the 63% for the dog, and then we just take the log of it. And then we will get minus 2.1 and minus 0.2. And that is the loss for this prediction. And that makes sense, right? Because the ground truth will be, we have to assign 1 here. That means we have assigned 100% for this dog, and that seems the ground truth for us, right? If you take that log of 1 into put up your calculators and then you input the numbers, you will get 0 loss from that. That means the model is doing a perfect prediction. On the other hand, we put 0 on this one, right? And then that will be indicate a very huge number, that is infinity. That means we're telling the model that is you are doing really bad job, and you should try to improve from that, right? So how can we improve the models? Well, that's the improving of the model refer to optimization, and we have a very different approach for these matters. The first approach is we can actually try to pick some weight, and then we calculate the loss, and then we pick the next set of weight and to see if it performs better. If it does, then we will keep picking the best weight. But this is not very efficient, right? Because you're just randomly picking some weight and calculate the loss. And then the second approach is we can maybe start to picking a point first, and then we slightly increase maybe 1 weight, to see if the loss improved or not. If it's improved, then we will try to increase the loss that weight a bit more to see if it's further increase or decrease the loss, right? And this could work, but in our example, we show that there's only 4 pixels that could work, but in reality, we have thousands of weights, and these weights will be have thousands of thousands as well. So imagine you have to tune the weight one by one, and this is not good as well. It takes too much time. So the third approach is to the gradient descent. And if you still remember, like in high school mathematics, if we just plot the weight and then we get the loss, and then thus, for example, this is the whole graph we have. Like imagine we have a supercomputer, we calculate all the weights and we calculate all the loss. But in this graph, we can actually just see that if we can just calculate the slope of this initial weight, and then we can kind of see the gradient, right? The gradient, it means the slope of this graph and I mean this curve, right? So if we moving into the gradient of direction, then that will eventually be reaching the global minimi, which means we try to minimize the loss here. So the direction of the weights will be the gradient of this particular point. And if you remember the mathematics in high school, that is basically we can just calculate the differentiation between that point and respect to the loss. And in the 3D matters, and then we can just imagine you're on a hill, and then you are trying to step down from the hill, but you didn't know, you can't see everything like around you. And what you can do is maybe you step your foot a bit forward to feel like which way is going down. And then after you find the way, the steepest way, then you take a tiny step and tiny step, a tiny step until you reach this bottom, which you are going down from the hill. And this point is the minimize the minimum of the loss you want to reach. And the alpha here is just a stepping you want to take from the direction of the gradients. And this alpha usually will be very small. Is usually people would take around 0.02 because you don't want to like take a big step, right? Because if you take a big step, you probably will miss some small step that will be leading to the global minimum, right? If you take a too big step, that means you are basically jumping off from the cliff, which is not good for your model. For machine learning model, you want to take a step tiny by tiny so that you can get the full features of the process. So we have talked about the linear classifier, and this is another metaphor for the nuance that described in deep learning. So we can take this as the linear classifier, so that we have many features, and then we assign the weight of each features. And because we want to pass it into the next layer, that means we cannot use after we have the weight assigned to each pixel, we pass it into a softmax, right? But this will give us a probability distribution. Usually this layer will be at the end, but because we want to pass it into the next neurons, so we will use something called activation function. The activation function is just a function that can squeeze the numbers into a real number between 0 and 1. And why do we need to do that? Because if we look at our example here, after we apply this weight here, we will get a score, right? Imagine if we pass it to the next neurons, the score will keep multiplying. At the end, the number will be very, very huge. And this is, you don't want this in computer science in general. If a number get too great, you will get like overflow memory. So what it does is it's trying to squeeze into a number between 0 and 1. So if the x-axis is the value, and then the output will be on the y-axis. So as you can see, no matter how big is the value, it will always the value of the output will always lie between the 0 and 1. And this is used to stabilize the learning process, as well as because we are introducing nonlinearity into the model can learn to, okay, if this feature is not good enough, we just deactivate by making the activation to produce 0. If we wanted these features, we will make the activation function to create to output a 1 at the end. And there are also many different type of activation function, but the sigmoid is the most classic one. And then we have 10H, reload, and then more activation outside here. But in most common nowadays, the model will usually use reload because it is a very fast activation for the model to converge. And yeah, the deep learning, it means that we stack different set of neuron together, and then usually the deeper the layer it is, the more features it can capture. And then one of the very classic architecture is the convolutional neural network. And because we have talked about we can stacking the neuron, why don't we just put multiple classifier together so that we can process the image in a faster way? So in this example, we will have the pixel. For example, the input for this neural network, we have the weight times height times the depth. Weight usually will be the height of the image, the width of the image, and the depth is usually 3 because we have the RGB 3 channel, right? And then we have 4 other hyperparameters. The K is the number of filters, and then the filter size is the half. If we have, for example, if we have a filter size of 3, that means we have 3 times 3 filter that filter the image. And then stripe is the step that the pixel that has to skip to the next pixels. And if we have 2 here, that means we are skipping 2 pixels to the next features. And then we have the paddings. The padding is the border of the image that we maybe want to add in so that we can examine the border of the image. And I know it's a bit confusing here, so that I have a really good demonstration for you. And well, so right now we have image 5x5, which is the purple image at the middle. And then we have the padding, which is a 0 that around the image so that we can examine the border features of the image. And then right now we have 3 filters, and we have 2 filters, and then each filter will have a size by 3 times 3. And then we have the stripe of 2. So if you look closely to the action here, so the filter is skipping 2 pixels. So like the first one is here, and then the second one is here, right? So that is skipping 2 pixels. That will be having stripe of 2. So then we have the formula here is to calculate the output size of the pixels. So if you plug in the pixel and then plug in the dimension, then we will have 3 times 3 times 2. And this is what we get the output here. So the purpose of this convolution layer is, well, originally we have a 5 times 5 image here, right? After we apply the convolution neural network, and then we were able to extract an image that have 3 times 3 times 2. That's a lot of reduction here, right? So the convolution layer is, we can stack multiple convolution layer between them so that we can reduce the dimension of the image, and the output of this will be the features we want to get. So the weight of this filter will be first randomly initialized, and then we have the loss function to guide the way that which features we want to get. If we want to get this particular part of the images, we will assign a higher value of the filters. So in today's topics is we want to generate images, and one way we can do this is we try to create a function that can be mapping the training images and to create some samples, and this is called generative model. And I think a couple months ago, and OpenAI has released the Della 2, and it was very fascinating model. And what it does is you can input some text, and then the text will be converted into the image. And for example, if we put like this text is, we want to astronaut that ride on the horse, and then yeah, that's amazing. So in today's architecture is we want to create the generative adversarial neural network. So what it's trying to do is we have some random input factors. But factors usually they is 64 times 64 images, but for the sake of the computation efficiency, they usually flatten the image into just one mobile factors. And then after we input this factor into the model will generate some images. It could be very bad, it could be very nice, we don't know. But we pass these images to a second model, which is a discriminator, alongside with some real images. The discriminator will try to do a classification to classify which images is real and which images is fake. And then after, he will pass back the information to the generator. Oh, well, this is my score for this example. I can recognize this is a bad image. Can you do better? And then at the same time, it also reference to itself to improve its discrimination in real image and fake image. And this is the example of the generator. And it's nothing really fancy. It's the topic that we talk about. We have multiple of convolution neural network, and then we try to scale up the image into the size that we want. And these features will be captured in between each layers. And I think we can jump into the second part of the presentation. Is we try to create a generative model in Azure Machine Learning Studio. So the first thing we need to create is the Azure Machine Learning Studio. If you have logged into the portal, and you have to click on this bottle, like have a bottle icon on it. And after that, we have to create the workforce. Then and you have to enter your name for the model, and then you click on the create. And after a couple of minutes, then you should be able to deploy it. And then after your deployment is done, you go to the resource, you launch the studio, and you click on the start now, and then you create the file, and you name your file, and then you click create, and we are pretty much ready to go up. Yeah, and then you have to create a machine learning instance from here. Then remember you have to pick a GPU because this is a computation task for images. It requires GPU to train the model. And also remember if you stop using the model and you have to terminate the instance because they will keep charging for $2 per hour because we are using a really good graphic card here. And then after all set, I think it's ready to go. So, so that we have to first, I have created a GitHub repository here. So I'm going to paste it in the chat so that everyone can clone it. So if you open the terminal here, then you type in the command. I just posted in the chat box. Then we should be able to clone the repository because I already create one. So I'm just gonna create a test file here. The git clone. Yeah, it take a while to download all the images because they'll be possibly including a lot of images. I think that was like around 8,000 of the images from the arts gallery. So this is some of the example that we have here. And I'm not. All right. So, and then, so we should have this file in the main here. So this is the original of the model. I have trying to organize it in a way that we can just import the model and then call some of the API here to create the models. But if you look closely, the model itself, it is just a bunch of convolution layer and then stacking together. And then we eventually we have the image we want to produce is 64 times 64 times 3. The free channel will be the RGB. And all right, I think we can start it. And so first we trying to import the library we have here. And then after we create a new block here. So the first thing we want to do is to load the data, which will be the function that I'll create is to load images. And then the path to the images are here. So it's on the main page. So we put image and it should be low. Yeah, it takes quite a while because we are loading 8,000 images. And one of the best thing about the Azure machine learning model is you don't need to care about the dependencies, because when I try to train the model on my local computer, I have to install thousands of packages, and they have a different version. That might be having a conflict with other version. But in Azure Machine Learning Studio, they have all the packages installed for you. So you can just simply import the package you want to produce. And yeah, that's the image training images we have. We have trying to crop the image because I remember the original of the image is quite huge. So we try to crop it into 64 times 64, which the images we want to reproduce. And then the second step is we will create the generator, which I create a function, already create a function. So we simply name the generator with the netg, and then we call the generator and to device. And that should be create the, yeah. Okay. The device here means that if we look at the models, when I load the images, we have to set that CUDA here means that it's using the GPU. So we will use the GPU if the GPU is available, else we will use the GPU. I mean, we will use the CPU. And in our case, we have installed the computer using a GPU, so we can have the data loaded into the device. And here we have to put the model to the device as well. And after we initiate the model, we need to apply the weight that we have already initiated. And after that, we print the model, the architecture of the model. Yep. So this is our generator. And then the second step is we need to create our discriminator, which is similar to the first step, but we have to change it to this private later. Then yeah, I'm gonna change the name as well. Oh, yep. Oh, I forgot to change the name. Yep. Yep. So I can briefly explain the model here. So we have the input images as 64 and times 64 with 3 channels. Again, it's just bunch of convolution layer, and then we scale down into just to 1 dimension. From 64, we scale up to 64 to 128, and then 128 to 256. And then finally, we scale down from 500 to 1. And then we use the sigmoid function again to classify the if it's the real image or fake image at the end. Okay, after we create the model, we try to create the input factors, which will be some fixed noise. We have to create this variable as the fixed noise. And then again, we have to put the input vectors into the device, which is our GPU. And then we create our optimizer for the gradient descent. And then this will be the gap optimizer. And we have to put the network parameters into the models. And then we repeat this for the generator as well. So the optimizer is to govern the learning process to make sure is doing the gradient descent properly. And I think I misspelled here. Yep. Okay. So right now we can test the model. For example, we create a variable for effect image, and then we have the generator, and then we input the fixed noise into the generator, and then to see what we get the fake image, and we have to detach from the GPU into CPU. Okay. I think I also misspelled that word. Okay, so that's the initiation without any training. So it just something randomly creates images, and I don't know what it is, and that makes sense because we haven't trained the model yet. And then in this part is we trying to train the model, which we have to input the PyTorch. And then we have to have the image list over here that will be recording our training image. And then we define that a fixed function which will starting the training process. We will input the epochs is meaning how much we want, how long is the training process. And then we input the learning rate, and then we start with the index first. And then we need to create a variable to record the loss and the loss of the generator and the loss of the discriminator. And let's say we initiate as none. And then for each epoch in range of the epoch, the epoch is the total epochs we want to train. So for each epoch, we have to get the real image. So we have to, for each image from the data loader, then we will have to get the images from the data loader. which is the zero index of the real image, and then put it into device, which is our GPU. And then we will get the loss from the training process. Then we need to copy this. I think I misspelled here. And then we will get the loss also from the we try to train the generator, which I think I also misspelled here. And then we can print the stats. After each epoch, we will try to print the loss function. I mean, the score of the loss, the score of the discriminator, as well as the epochs we are going through. And then I think we are good to go. So that we, yes, and then we try to fit that. We input the learning weight, and then we input how many epochs we want to train. And it take a bit of time to initiate for the first time. And here I have some example that the training process. I have recorded the training process of the epochs. So that's the initiation of our images. And then I think I train around 6 hours, and I record every images. And then the models start learning the patterns. And after around 100 epochs, and you will start to see some images that looks like some of the images looks pretty real. And for example, this one, it looks like a scenery of that. And yep, so I already uploaded code into the GitHub repository. So you can have a look on the code. And then if you find any problems, feel free to send me a message. All right. I guess this is the end of my presentation. Do you guys have any question?
That was really good, Kelvin. I don't see any questions in the chat, but yeah, perhaps as you say, people might reach out to you afterwards. Maybe paste your LinkedIn thing in the chat so that they could connect to you on LinkedIn as well.
Yeah, sure.
I just want to say thank you so much, Kelvin. It's really an awesome presentation about. I just feel there's a lot of things involved in it. I'm just wondering if if your presentation is recorded. So I think I might need to rewatch it and maybe follow your steps to get some hands-on experience myself.
Yes, it is recorded, and let me just paste the YouTube playlist where it will appear later this week, so you can watch it again.
Yeah, that would be awesome. Thank you.
I was thinking I need to watch it again because yeah, there's a lot of content there, but also because your little dog is so adorable. What did you say the name of your dog is?
The name of my dogs? Yeah, my name. Yeah, his name is Donut.
Donut.
Yeah, because the colors look like a donut.
Oh, very cute.
That was awesome. Yeah. I had one question around when you're training the model. Do you know how accurate it usually ends up after like a few hours of training? Or
Because this is a generative model, it doesn't really have accuracy because the accuracy will depends on the discriminator, which you always try to. The model here is you are trying to maximize the loss on discriminator because you try to fool the discriminator, and at the same time you try to minimize the loss in the generator. So it doesn't really have an accuracy in that case because you're not doing a classification in that case, but in this example.
yeah, right. No, that makes sense. Thank you.
I also saw a question about is the Tesla K80 is the first GPU you recommend trying out? Unfortunately for the free trial, I mean from the student free trial, you can only pick this kind of GPU because the other GPU will cost a bit more. But I think this one is good enough to start with.
Yeah, but be real careful when you're using machine learning and GPUs because it's very easy to rack up a huge cost very quickly. So what I say for everything is try and delete everything at the end of every session that you've created until you're confident with understanding costs and how the charging and billing works and things. Just, learn first of all, play with it and delete everything at the end of every session, all your resources. And then you never have any shocks.
Yeah.
Actually go through and delete something. I know that's sometimes it can be like a bit complicated. Do you mind running through that?
Yeah, deleting it is, when I first was doing it, it was difficult to understand, but you can view all of your resources. And then if you delete all of your resources, that's the easiest way, and make sure there's nothing showing. So yeah, you have to look at the all resources view as opposed to the most recent view, because the most recent view will show you things that you have already deleted. But yeah.
Yeah. So I can quickly show you it's very easy to terminate the instance you create in Azure Machine Learning. So you have to just press this and then it will stop the computing. So remember to stop it after you're done because it's costing $2 per hour.
Sometimes stopping is not enough if the service that they have got is, some sort of SaaS or PaaS service. Sometimes you're being charged for the service whether it's running or not. So that's why I say delete the things completely rather than just stopping them, because what is it? Cognitive search, very expensive, and it's a service.
Would you be able to load up the resource view? Because I know that's something that I did when early on. I ended up using up my entire $100 very quickly because even though I terminated it, it was still running in the background. Maybe that's something useful we could run through, is just how to delete it.
Well, there he is in the Azure Machine Learning Studio, not Azure Portal. So I don't know whether it's you don't have the Azure Portal open as well, right, Kelvin?
Yeah, I don't have it, but it should be shown on the portal as well. And I think, yeah, you're right. You have to delete the resources in the Azure portal as well. Let me quickly go to the Azure portal.
I think that's it there. If you click on the home
the home here, right?
Yeah.
Yeah.
And then the all resources, see that,
So each thing is its own resource, and then you'd have to delete it completely in order to stop it.
Yeah.
Yeah.
So you make the most of your $100.
Yeah. Easy as that. Well, easy as that in that it makes you confirm and you have to say yes that you're sure, but then they would all be gone.
Maybe final question is, if I wanted to learn more, where would you recommend I go? Or what do you think of like next steps?
I think my presentation for today is a bit too rushed, and then because there's too much information in it. So I would recommend the Introduction to Machine Learning by Andrew. And then I will post a link when we upload the presentation as well. And then yeah, those videos, you can find those videos in YouTube. I think he's a very good teacher in machine learning, and that's how I started as well. So it's the Introduction to Machine Learning by Andrew.
And I, of course, recommend the AI Fundamentals Learning Path from Microsoft Learn and the AI Engineer one and the Data Scientist Learning Paths. All three of those would have a lot of machine learning heavy content within there. And what I like about the Fundamentals one is it starts very, with very easy stuff that anyone can do, but it is in fact stuff that you can build almost immediately. So although it's for beginners and you don't need any background knowledge, it gives you stuff that you can immediately build. Cool. Then thank you, Kelvin. That was an excellent job you've done there, and I look forward to seeing more more classes with Kelvin, because yeah, that was wonderful. Yes, thanks everyone, and I will stop recording now and let you all go back to your days.